You know, whenever we sit down to talk about the cutting edge of artificial intelligence, there is really one letter that completely dominates the conversation for you guys listening.
Right, the T,
The T in GPT.
the transformer.
Exactly, the transformer. It's basically the celebrity architecture of our time.
Oh, absolutely.
I mean, it's the engine behind ChatGPT, Claude, Gemini. Pretty much every major breakthrough we've seen in the last 5 or 6 years relies on this specific way of processing information.
And for very good reason.
Yeah.
I mean, it completely transformed, and no pun intended, the way machines understand human language.
Right.
It allowed for parallel processing. It gave us much deeper context. And honestly, all the generative abilities we just take for granted today.
And this is a really big but that we're going to unpack for you on this deep dive today. The transformer isn't perfect.
Not at all.
I was reading through the research for this deep dive, and it really feels like we are hitting a ceiling, or maybe not a ceiling, but a really heavy backpack that the transformer just constantly has to carry around.
That's a very apt metaphor, actually. The transformer has a massive efficiency problem.
Memory, right.
Specifically memory,
Yeah.
Because as you and the developers out there try to push these models to read longer and longer documents,
Yeah.
I'm talking entire books, massive code bases, entire legal archives, that backpack gets so incredibly heavy that the model essentially slows to a crawl.
Or it just outright crashes.
Right. It just runs out of memory entirely.
So today our mission is to do a deep dive into a brand new model that claims to actually solve this. It's called Jamba.
Jamba, yeah, developed by AI-21 Labs.
And the headline claim here is honestly kind of wild. I had to read it twice.
It's a big claim.
They've built a model that can handle a context window of 256,000 tokens, which is just huge.
Massive.
And they say it fits on a single 80-gigabyte GPU.
Which, for anyone listening who tracks hardware requirements for large language models, that sounds physically impossible for a model of this size.
Right. It sounds like an absolute magic trick. So that's the mission today. We are looking at their paper, which is titled Jamba, a hybrid transformer Mamba language model. And we're going to figure out how they pulled off this magical shrinking act for hardware requirements by mashing up two completely different types of AI brains.
Right. Architectures that, honestly, if you look at them on paper, just shouldn't work together.
But they do it to solve this memory bottleneck without the model getting dumber.
And it's a fascinating case study because it represents a real shift in the industry from pure architectures to hybrid ones.
Yeah, moving away from the one-size-fits-all idea.
Exactly. We're moving away from the idea that one single algorithm can just do everything perfectly.
So let's start with the villain of the story here, or at least the core problem we're trying to fix. Why do transformers get so heavy in the first place?
Well, it comes down to how they read.
I always visualize it like reading a book. If I'm a standard transformer and I'm on, say, page 500 of a mystery novel, to understand the first word on that page, I don't just rely on my general memory of the plot.
No, you don't.
I have to actively rescan and cross-reference every single word on the previous 499 pages just to read that one new word.
That is painfully accurate. In technical terms, we call this the attention mechanism.
Right.
The model literally builds a matrix of mathematical relationships between every single token and every other token that came before it.
And they call that the cache, right?
Yes, the key value cache, or KV cache.
And this KV cache, it just grows and grows.
It grows quadratically, and this is the absolute killer for transformers.
Because it's not a straight line.
No, if you double the length of the text you're feeding the model, the computational cost doesn't just double, it quadruples.
Wow.
If you triple the text, the memory cost goes up 9 times.
So it spirals out of control almost immediately.
Exactly. It's an exponential explosion of memory usage. Let's look at a standard transformer like Llama 270B. If you wanted to process that 256,000 token context we mentioned, just the memory required to hold that conversation history, the KV cache alone would be about 128 gigabytes.
Wait, 128 gigabytes just for the cache?
Just the cache.
So that doesn't even count the actual model weights.
Correct. And since a top-tier industry GPU like an NVIDIA A100 usually tops out at 80 gigabytes,
Yeah.
you literally cannot run that context on one card.
It's physically too big.
You need a cluster of GPUs just to hold the memory of what you're currently talking about.
So enter the challenger here, the Mamba architecture.
Llama, yes.
We've touched on this briefly in past deep dives, but let's really define it for you guys today. How does Mamba solve the rereading the whole book problem?
So Mamba is based on what's called a state space model, or SSM.
SSM, right?
And it approaches memory completely differently. instead of keeping a perfect high-definition library of every word you've ever said. Mamba works a lot more like a human taking notes.
Taking notes, how so?
Well, imagine you're reading that same mystery novel. As you read, you aren't memorizing the text verbatim word for word.
Oh, no, of course not.
You're updating a mental model as you go, a hidden state that summarizes the story so far.
Like the butler is suspicious or the gun is in the drawer.
Precisely. When you turn the page, you carry that summary forward, but you don't need to physically look back at the raw text of page 1.
So it compresses the history as it goes.
Exactly. And because it's a compressed state, the memory requirement is constant.
Constant.
Yes, it doesn't matter if you've read 10 words or 10 million words.
Yeah.
The amount of RAM Mamba needs to generate the next word is effectively exactly the same.
So it's linear.
It's linear time, not quadratic.
Okay, well, that sounds like the holy grail of AI right there. Infinite context with zero memory penalty. So why haven't we just thrown out all the transformers and replaced them entirely with Mamba?
Because compression always has a price.
Oh.
Think about your mental summary of that mystery book. If I stop you on page 500 and ask, what was the exact third word on page 42? You can't tell me.
Right, I summarized it away. I lost the resolution.
Exactly. Pure Mamba models are incredibly fast and memory efficient, but they historically struggle with what we call in-context learning.
Learning from the prompt.
Right. If you give them a complex prompt with very specific examples and say, follow this exact pattern, they sometimes get a bit fuzzy.
Fuzzy.
They capture the vibe of what you want,
Yeah.
but they miss the precise syntax because they can't explicitly look back at the raw data you just gave them.
Okay, so we have the transformer, which is brilliant and precise, but mathematically obese and incredibly slow for long text.
Yes.
And we have Mamba, which is athletic, incredibly fast, but maybe a little forgetful with the fine details.
And that perfectly sets the stage for Jamba, the hybrid.
This is where the paper gets really interesting to me. They decided to mix these two architectures to get the best of both worlds.
A hybrid decoder.
But it's not a 50-50 split. They ran a bunch of tests, ablation studies to find the perfect recipe for the layer cake. And the ratio they landed on is actually quite surprising.
It really is. They settled on a ratio of 1:7.
One transformer layer for every 7 Mamba layers.
Exactly, 1:7.
That seems risky to me. I would have thought you'd need way more transformer layers to keep the model smart. But they're saying just a sprinkle of attention is enough.
It turns out, yes. And this ratio tells us something really profound about how language modeling actually works under the hood.
What's that?
It suggests that for the vast majority of processing, about 87% of the layers, you don't actually need that high-resolution, expensive attention.
Wow, 87%.
The efficient running summary of Mamba is perfectly adequate for handling the general flow and syntax of the language.
So you only need the transformer to basically stop and check your notes every once in a while.
Precisely. The Mamba layers handle the heavy lifting of moving efficiently through the text. And then every 8th layer, the transformer block kicks in and says, okay, let me scan the entire raw history with perfect clarity just to make sure we haven't missed a specific reference or a specific pattern.
It's like skimming a textbook efficiently, but stopping to reread a critical paragraph carefully every chapter to ensure you're actually tracking the core concepts accurately.
That's the perfect way to visualize it.
Yeah.
And the impact on the memory requirement is just massive. Remember that 128 gigabytes of cache we needed for the pure transformer?
Right, the heavy backpack.
With this Jamba architecture, because 7 out of 8 layers don't need that massive cache, the requirement for 256,000 tokens drops to just 4 gigabytes.
Wait, 128 gigabytes down to 4?
Yes.
That is an absolute miracle for GPUs.
That is an 8 times reduction compared to similar long context models, but specifically for that cache footprint, it completely changes the game.
That's the difference between needing a massive server rack and literally running it on a high-end gaming PC at home.
It effectively democratizes long context AI. Suddenly, you don't need a massive corporate hardware budget to process a novel-length document. You can do it on commodity hardware.
But hold on, because there is a third ingredient in this layer cake we need to talk about.
The MoWeave.
Right, we've got Mamba for speed and attention for precision. But Jamba is a massive model. Overall, 52 billion parameters.
It is a big model.
Even if the memory is perfectly efficient, usually a 52 billion parameter model is going to be slow just because of the sheer amount of math required to run it.
That's true. If you have to calculate 52 billion numbers for every single word you generate, it's going to drag no matter what.
So how did they get around that computational bottleneck?
They use something called MOE, or Mixture of Experts.
We hear this term thrown around a lot in AI lately, specifically when people talk about Mistral or GPT-4.
Yes, it's becoming very popular.
But let's break it down in the context of this paper. How does MOE actually work in Jamba?
Think of a traditional neural network, like a general practitioner doctor who tries to literally know everything about medicine. Every time you have a problem, you consult this one massive brain. Every single neuron fires for every single question. It's thorough, but it takes a massive amount of energy.
Makes sense.
Mixture of Experts changes that architecture completely. Instead of one giant block of generic neurons, you break the network into specialized subnetworks.
The experts.
Right. In Jamba's case, they have 16 distinct experts applied to the multi-layer perceptron layers every 2 layers.
So like one expert for coding, one for writing poetry, one for math.
Roughly speaking, yes, though, the model naturally decides the specialization itself during training.
Right.
But here is the real magic. For any specific word being generated, a router mechanism kicks in and picks only the top 2 experts that are most relevant to that exact token.
Oh, I see. So if I'm asking a question about a Python script, it wakes up the coding experts but leaves the poetry experts completely asleep.
Exactly. So while Jamba has 52 billion parameters of total knowledge sitting in its brain for any single calculation, it only uses or activates 12 billion parameters.
That is a huge distinction. 52 billion total, but only 12 billion active compute.
Yes.
So you get the vast storage capacity and knowledge base of a giant model, but the speed and running cost of a much smaller model.
It cleanly decouples capacity from compute. You can make the model smarter and bigger without making it slower.
Right?
And when you combine that MOE compute efficiency with the Mamba memory efficiency, you get Jamba.
It's basically efficiency stacked on top of efficiency.
It really is.
But I want to go back to the smartness factor for a second, because usually in engineering, when you start cutting corners, compressing memory with Mamba, skipping parameters with MOE, you pay a tax. The model gets dumber.
And that was the big risk the researchers faced. And the paper actually highlights a really funny failure mode that proves exactly why they needed the hybrid approach and couldn't just use Mamba.
Yes, the IMDb study. I loved this part of the paper. It really illustrates the Mamba problem perfectly.
So they discuss an ablation study they did with pure Mamba on the IMDb movie review data set.
So they took out all the transformer layers.
Exactly. No attention layers at all, just pure Mamba. And they gave it a standard task. Here are 3 movie reviews. Review 1 is positive, Review 2 is negative, Review 3 is positive.
Standard few-shot prompting. Just follow the pattern I gave you.
Right. Then they gave it a 4th review and said, label this.
And what happened?
Well, the pure Mamba model read the review and clearly understood it perfectly. But when it came time to actually output the label, it wouldn't say positive or negative.
What did it say?
It would output things like 3 out of 10 or very good or 2 thumbs up.
Which is hilarious because it's not factually wrong.
No, it's right.
It understood the sentiment perfectly. It just totally failed the strict formatting constraint.
Exactly. It couldn't copy-paste the strict pattern from the examples in the prompt. It captured the gist that the movie was bad, for example, but it lost the specific instruction to use the exact word negative.
And this is what you technical folks call induction heads, right?
Yes. Induction heads are specific circuits in a neural network that allow for precise pattern matching and copying. They essentially act as a function that says, I saw this exact sequence in the past. I see it again right now, so I should copy exactly what came next.
Like a macro.
Exactly. Transformers are natively amazing at forming induction heads because they can constantly look back at the raw text in the prompt.
But Mamba can't.
Right. Mamba, with its compressed state memory, struggles to form these induction heads on its own.
So by sprinkling in those few transformer layers every 8th block...
They effectively gave the model reading glasses.
Reading glasses, I like that.
And the researchers actually visualized this attention mechanism in the paper. It's figure 8 for you guys playing along at home.
Yeah, I saw that chart.
You can visually see the model explicitly looking back at the specific labels in the few-shot examples just before it generates its final answer.
So the transformer layers are there specifically to handle that strict copy-paste logic that Mamba just can't do natively.
Correct. And that is the absolute aha moment of the whole paper. You don't need the whole brain to be capable of induction. You just need a small, specialized part of the brain to handle the pattern matching, while the Mamba layers handle the bulk of the reasoning and the information flow.
That is so elegant. So let's talk about the results. Does this Frankenstein monster of an architecture actually work in the real world?
It does.
We know it fits on the single GPU. We know it's fast. In fact, the paper says it's 3 times faster in throughput than Mixtral 8x7B for long contexts, right?
Yes, 3 times faster throughput.
Does it hallucinate or lose track of things?
The test, they ran the ultimate AI stress test the needle in a haystack evaluation.
Oh, I love this test. This is where you hide a random, like the secret password is blue7, right in the middle of a massive amount of random text, right?
Yes. They filled up that entire 256,000 Tolkien context window, which again is like reading 5 novels back to back, and they hit a specific fact somewhere in there.
And then they asked Jamba to find it. And usually pure non-transformer models fail this, right? Because of that compression we talked about earlier. They just blur out the tiny details.
They do. But Jamba scored perfectly.
Perfectly. As in 100%.
Yes, it retrieved the needle perfectly, regardless of where it was placed in that massive context window.
Wow.
This completely confirms that the 1:7 ratio is sufficient. The transformer layers provide enough high-fidelity recall to totally offset the compression of the Mamba layers.
That is incredibly impressive. It basically says we really can have our cake and eat it too. We get the massive context without the massive memory cost, and we don't lose the fine details.
And it holds up on the general academic benchmarks, too.
Oh, really?
Yeah, on things like HelloSwag for common sense or ARC and MMLU for reasoning. It performs right alongside Llama 270B and Mixtral.
So no intelligence tax.
None. You aren't trading IQ for efficiency. You're getting the efficiency essentially for free just by being much smarter about the architecture design.
I want to take a moment to geek out on the engineering side a bit.
Let's do it.
Section 5 of our notes for this deep dive covers engineering quirks. Because I imagine building a hybrid like this isn't just snapping Legos together. Things must have broken along the way.
Oh, absolutely they did. When you're pioneering a completely new architecture like this, you run into problems that literally no one has ever seen before.
Right.
One of the most interesting findings they shared was about positional encodings.
Break that down for us. What is a positional encoding?
So in a standard transformer, the model actually processes the whole sentence at once. It's entirely parallel.
Okay.
So if you feed it the sentence, "the dog bit the man," it doesn't inherently know that the word dog came before the word man.
Because it sees them all simultaneously.
Exactly. So you have to mathematically stamp each word with a number. Position 1, position 2, position 3.
Like numbering the pages of a book so you can read them in the right order if you accidentally drop them on the floor?
Exactly right. Standard models use something called ROPE, rotary positional embeddings, to do this.
Ropey, yeah.
But Mamba is sequential by nature. It reads word 1, updates its state, then reads word 2.
So it experiences time linearly, just like we do.
Right. So the researchers asked, well, do we actually need the page numbers anymore?
And what did they find?
They tried training Jamba with explicit positional encodings and without them. And they found that adding them made absolutely no difference to the performance.
So they just left them out completely.
They stripped them out entirely. The Mamba layers naturally handled the ordering of the sequence, and the transformer layers just figured it out for the context Mamba provided.
I love that. It's a cleaner, simpler design.
Very elegant.
But I also read in the paper about some major stability issues. The model was basically throwing tantrums during the training process.
Yes. And this is the dark side of Mamba that we are just starting to understand.
Ooh.
When you scale these state space models up to billions of parameters, the internal values, the activations, can get incredibly volatile.
Volatile.
They can essentially spike out of control. You get these massive loss spikes where the model gets totally confused, the error rate shoots through the roof, and the training run essentially crashes.
That sounds expensive.
Very. It turns out that large Mamba layers are highly prone to these internal mathematical explosions.
So how did the AI-21 team tame the beast?
They had to use a specific type of normalization called RMS norm.
Root means square normalization.
Yes, but the real key was where they put it.
Yeah.
They had to insert these normalization layers right inside the Mamba blocks themselves to act as a regulator.
Like a pressure valve on a steam engine.
That is exactly what it is. It keeps the mathematical signal flowing through the network strictly within a healthy, stable range.
Wow.
Once they added that specific RMS norm, the training finally smoothed out. It's a small detail, but honestly, without that specific engineering fix, we probably wouldn't be talking about Jamba today.
It simply wouldn't have trained.
It would have kept crashing.
It's such a great reminder for you guys listening that AI research isn't just high-level theoretical math. It's also gritty, hands-on engineering, literally figuring out where to put the pressure valves so the billion-dollar engine doesn't blow up.
That is the reality of the field right now.
Yeah.
We have the grand theory, but the actual implementation is full of these tiny, critical, empirical discoveries.
So bringing this all together, Jamba is open weights.
Yes.
AI-21 Labs released it under the Apache 2.0 license. This isn't just a theoretical paper we're reading about.
Not at all.
People can actually download this model right now and use it.
Which is a huge win for the open source community. Because we're going to see developers all over the world experimenting with this 1-to-7 ratio.
Tinkering with the recipe.
Right. Maybe they'll find that a 1-to-10 ratio works better for generating code, or maybe 1-to-5 is better for highly technical medical texts.
It really challenges the status quo, doesn't it? Because for the last 5 years, the answer to literally every problem in AI has just been make the transformer bigger.
And obviously buy more GPUs.
Right, just throw more hardware at it. But Jamba is saying, no, you don't need more hardware. You just need to change the architecture entirely.
Yes.
And that leads me to my final thought for today, and I'd really love your take on this before we wrap up.
Okay.
If Jamba proves that a hybrid model is tangibly superior in efficiency and just as smart, are we currently looking at the beginning of the end for the pure transformer?
That is the big question.
Yeah.
And honestly, I think we are looking at the dawn of the era of compound AI.
Compound AI?
Yes. We're finally moving away from looking for one God architecture that just natively does everything.
Right.
Instead, we're starting to build systems where the transformer is basically just a specialized plugin. It becomes the pattern matching module inside a much larger, more complex brain.
And Mamba becomes the memory module.
Exactly. Maybe we use Mamba for the long-term memory, and the general reasoning we use small transformers just for short-term attention and induction, and maybe there's even a third architecture we haven't invented yet for specific creative tasks.
It starts to look a lot more like the actual biological human brain, doesn't it?
Yeah, it really does.
I mean, we have different regions of our brain specialized for different tasks. We don't use our visual cortex to do complex math.
That is exactly the direction we are heading. Jamba proves that you can successfully mix these disparate architectures and get a highly stable, high-performance result.
Yeah.
It opens the door to pushing that ratio even further. Could we do 1-to-20? 1-to-50.
And with every step in that direction, the hardware requirement drops even further. The context window opens even wider.
Exactly.
We get closer to models that can literally read entire libraries on a single commodity chip.
For years, we have been trying to break the quadratic bottleneck of attention. Jamba just showed us the exact hammer to break it with.
It's an incredibly exciting time. I, for one, will definitely be watching the leaderboards closely to see what the open source community does with this absolute beast of a model. But that is all the time we have for today's deep dive into Jamba. Thanks for listening and exploring this with us, and we'll catch you on the next one.
Goodbye.